Hello, and welcome to you all to this session. And I'm assume I am audible to you all. If not, then you can write in the chat box. So we will start our session. So I welcome you all to this tutorial session on power system engineering. It will be taken up by me, Mohammed Owais Khan, the Prime Minister Research Fellow at the Department of Electrical Engineering. So before we start our lecture, you would have gone through the week 4 lecture, and you have gone through in which you have gone through the basics of various things which has been discussed discussed over there. Okay, and what we will do here, we will solve some problems and discuss some problems, and then we also discuss in brief various topics. So here I what I will be going to discuss is corona. Okay. So what is a corona? It is the ionization of air in the surrounding areas of conductor. Okay, mainly power. Okay. What happens here is that it is generally defined as a self-sustained electrical discharge. Okay, and it happens when field is intensified beyond a particular value. Okay, so there is a this value is generally known as critical voltage. We will derive that equation in here. So what happens is that the electrons which are around that conductor in the space becomes gets as the potential of the conductor increase, the gradient around the surface of a conductor increases. This lead to the corona, and uh, it is followed generally by a hissing sound. Okay, and an ozone gas is also found which can be detected by its characteristic color. So this is the it has various it has various disadvantages, and it also affect on various conditions like atmospheric conditions, electrical factors, how much gradient is going to develop, and also on the atmospheric factors, and about it also depends upon the conductors. Okay, and these corona leads to a loss which you know as corona loss, and its formula is generally given described as 241 into 10 raised to the power minus 5 f plus 25 divided by delta under root r by d Vp minus Vo square. It is in kilowatt per kilometer per phase. Okay. Delta is delta is the air density correction which relates it to the atmospheric conditions. And Vp is the operating voltage and Vo is the critical disruptive voltage whose value we are going to derive here. So basically you can see here it depends upon the air density factors, electrical factors, also upon the diameters and the radius and the distance between the conductors. So the factors affecting corona losses. So it is a corona loss expiration. Okay, and this is generally, so first we will discuss the factors. The first one is the electrical factors. As you can see here, the corona loss is directly proportional to F plus 25, or we can say it is directly proportional to F. So basically, the higher the frequency of operation, higher the frequency of operation, more will be the corona loss. Okay. And it also depends upon the waveform of the supply. How may waveform of the supply means how smooth it is. Mainly, if it does not contain any harmonics, the losses will be less. But it contains any harmonics, like in AC, we generally have third harmonics there. In AC, we generally have third harmonics in our waveform supply. So basically, PAC, power corona loss, will always be greater because it contains harmonics. But on the other hand, DC does not have any harmonics, and so what will happen here is that it will have lesser corona loss in comparison to AC base. Okay. And also, if somehow we have an ideal waveform where is only 50 hertz frequency is there, which is not quite possible, because in general practical there always the third harmonics will be there in the waveform. But somehow we get a waveform which have 50 hertz only, then that waveform will produce corona loss will lesser than an idea than a practical AC waveform which have all third harmonic, because the presence of these harmonics will uh, increase the corona losses. And also it depends upon the atmospheric pressure, atmospheric conditions, or we would say atmospheric factors. Okay. So basically, we know that it is directly proportional to 1 by delta. Okay, so the lower the value of delta, higher is the P loss. Okay, and there is also one thing here which you should know that presence of, for for low values, for low values of corona, the pressure should be low, and the temperature must be higher. Okay, for therefore, sorry, just a second, for low values of delta, actually, for low values of delta, just a second, the pressure should be low and temperature must be higher. That's why the corona, for low values, the corona losses will be higher. The corona losses will be higher in hilly areas. Okay, in comparison to plain areas. So these are some of the factors. Also, there is another factor which depends upon the conductors. And you can clearly see in the expression is it directly proportional to R by D, and also losses is directly proportional to V minus VO square. Okay, VP minus VO square. VP is the operating voltage. So basically what happens here is that square root of the size means larger the dia of conductor, larger the dia of the conductor, larger will be the losses. But but we know that VO is approximately VO, which is critical disruptive voltage. We will see here in this, it is directly proportional to the size of the conductor when we derive that expression, and hence the larger size of the conductor will be, hence what happened here is that larger the size of the conductor, larger will be the critical disruptive voltage, and hence smaller will be the difference. So it is found that effect of second proportionality is much more on the first, on the corona losses. Therefore the larger the size, therefore larger the size of corona, what happens, the larger the size of conductor, sorry, it will lead to a lower in the lower corona losses. Okay, so these are some of the factors on which this defined. Like it also depends upon the surface conditions, means I will write it down here, surface conditions. Okay, so what happens here is that the disruptive voltage will be lower when there is dirt or anything like that on the is deposited on the surface. So what happens here is that Vp minus Vo whole square, if it gets lower, then whole expression will get higher value, so P losses will be gets increased. Okay, so now another here is that now another thing is it also depends upon the shape of conductors. Means if there is any conductor which has a steep size, like for and there is any another conductor which is a cylindrical conductor which we generally use. Just a second. Okay. So for steep, the corona losses will be higher, but for the uniform cylindrical conductor, the air or the field ac- across field around the conductor is uniform. So that's why the losses in the cylindrical conductors, the corona losses, are very much lower. Okay. So we will solve some question. Before that, I want to, derive an expression for the critical disruptive voltages. Okay. So first of all, critical disruptive voltage. Okay. So let's assume a single phase transmission line. Okay. And their radius is R. Okay. So R is the radius of each conductor. Okay. And D is the distance between them. D is the distance between them. Or and we know that D is very much higher than the radius of the conductor. Okay. Since it's a transmission line of single phase, so there will be plus Q, let's say here, and minus Q will be here. Okay. And the operating, and let's say this is the neutral phase, neutral plane, and V is the voltage operating. Okay. So with respect to the neutral, for let 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 me name it A and B. So what happens here is that we will calculate a field due to A and B at a distance, let's say from A it is X, and from B it is D minus X. So first of all, E, electric field due to A at point X from itself. Okay. So let's say it is EA, which is equal to Q upon 2 pi epsilon naught X. Let's put this equation number 1. Then electric field at point D minus X from B conductor. So EB is equal to Q by 2 pi epsilon naught D minus X. Okay. Now what happens here is that due to this A, the field direction will be like this, but due to the minus Q, the field direction will be like this. So basically at that point, the addition of both field will be done. Addition of both EB and EA is equal to, let's say, EX. Okay. So EX is equal to Q by 2 pi epsilon naught X plus Q upon 2 pi epsilon naught D minus X. If we rearrange this, we can write it here like 1 upon X plus 1 upon D minus X. Okay. Now, this is the electric field, and we know the formula to calculate potential difference. Potential difference is equal to V equal to minus E dot dx from d minus x. Let me put a generalized statement first of all. Okay, it will be a generalized statement is minus EDR from R1 to R2. Okay, so the potential difference here, potential difference between the conductors will be V is equal to minus D minus R to R E dr, or we can flip the limits, we can write E dr, E dx, because here the expression is in x. So from where to where we are going to integrate? From this point to this point, we are going to calculate the potential difference. So what is E? Q R to D minus R. E is Q 2 pi epsilon naught 1 upon x plus d minus x dx. So integrating, we get v is equal to q upon, and if we put the limit, q upon epsilon naught, for this it is log x plus, sorry, just a second, this is minus, okay, minus log d minus x, and we are going to integrate from where r to d minus r. Okay, this is actually r to d minus r. Okay, so here if we put this in this expression and simplify that, you will get q upon 2 pi epsilon naught 2 log d minus r by r. Okay, like here first we will put the log here in this, so it will be, let me solve it for you, it will be easier. It will first of all log d minus r, okay, minus log r, then log d minus d plus r, okay, then minus plus log d minus x, in place of x it is r. Okay, so it will cut it down, and what it will be q upon 2 pi epsilon naught 2 times log d minus r by r. So if we cancel out 2, then v will come out to be q by 2 q by pi epsilon naught log d minus r by r. Let's say this equation is 2. Okay, now as I have already told you, d is very much greater than r, then we can say here d minus r is generally equal to d. So rearranging this equation, rearranging this equation what we will get, V is equal to Q upon pi epsilon naught log D by R. Okay, by adjusting this assumption, yes, D minus R is generally equal to D because the distance between the conductors is very much greater than the radius of the conductor. So this comes out to be third equation. Okay, now we know that we just calculated the gradient at any point, which is electric field, is E is equal to, we just calculated Q upon 2 pi epsilon naught 1 upon x plus 1 upon d minus x. E is equal to Q upon 2 pi epsilon naught d minus x plus x upon x into d minus x. It will be equal to Q upon 2 pi epsilon naught d upon x d minus x. I hope it is quite understandable to you. Now, if we substitute the value from Q from the above equation, what we will get here? We know that here Q is V pi epsilon naught log d by R here. So put this value in here, we get E is equal to what we will get, pi epsilon naught, I think just a second, pi epsilon naught V divided by log d by R, okay, into 1 upon 2 pi epsilon naught into d by x into d minus x. Okay, so if we cancel out some things over here, it will be like this. So basically, finally, E comes out to be V into D divided by 2 log d by r x d minus x. Okay, this here, these terms are leftovers. Okay, so at any point x, at any point x, Ex is equal to V d divided by x d minus x log d by r. Okay, and let's say it is v dash, so v dash is equal to v by 2. Okay, so now what is the v dash here? It is also, we can also say here, it is the line to neutral, line to neutral voltage of the system. Okay, now for any three-phase system, V dash will be equal to VL by root 3. Okay, now it is quite clear E is directly proportional to 1 by x. It means that when x is maximum, E will be minimum, or when x is minimum, E will be maximum. So x maximum minimum value will be at the, when x is equal to R, means it is at the surface of the conductor. So G max, which is the maximum gradient, is given by equal to E max when V dash D divided by when x is equal to R. So R D minus R log D by R. Okay, this is the value of the maximum gradient at the surface. Okay, and we already know that d minus r is generally equal to d. So we can calculate with this assumption this much. So g max will be equal to v dash r log d by r. So if we rearrange this, v dash is equal to r g max log d by r. So this is the critical disruptive voltage. This voltage, this v dash is equal to r g max log d by r. This voltage, this is critical disruptive voltage, and it is defined as the voltage at which complete disruption of dielectric will occur. And this value or this voltage corresponds to the gradient at the surface equal to the breakdown strength. जो gradient होता है, जो voltage होता है, ये correspond करता है to the gradient at the surface we just calculated. It also tells you that at this voltage the air will get breakdown, or it is near maximum to the breakdown strength of air. This is, and its value is denoted by it's denoted by G naught, and is equal to 30 kV per centimeter at 25 degrees Celsius and 76 mm of Hg at these atmospheric conditions. But for any other temperature, its value will get changed. So general or for general calculation, let's say that is G naught dash is equal to G naught into delta. Okay, and based on this, where delta is the air density correction factor, and empirically it is given by delta is equal to 3.92 b divided by 273 plus t. So for at any temperature pressure, its value will be calculated by this. Okay, this expression. So basically here B is the pressure which is in centimeter of Hg, and T is the temperature in degree Celsius. So if you want to calculate at any 27 degrees Celsius and 77 centimeter of Hg, you put these values in this, you will get the air density correction. Based on that air density correction, we can calculate the gradient by using the information by using this formula. Okay, so now moving on to this. Now these corrections will be incorporated in the critical disruptive voltage. So the modified formula to calculate disruptive voltage is V dash is equal to R G naught delta log D by R kV. So, this formula to calculate the disruptive voltage has incorporated the atmospheric conditions by using delta. Okay. Okay, now I think we will solve some questions regarding this, then we will move on towards other things. So let's me give you a one question. You should take pen and paper with you, and we will solve a question. It will give a better idea how we are going to calculate. So find the critical disruptive voltage and critical of, I think, just a second. Uh, I think other question I will give. Okay. Calculate the critical disruptive voltage and corona loss for a three-phase line operating at 110 kV, which has conductor of 1.25 centimeter dia arranged in 3.05 meter delta. Okay. Assume uh, air density factor at 1 point air density, just a second. Air density factor as 1.07 and and dielectric strength of air to be 21 kV per centimeter. So options are there. Okay. What we have to do here, we have to calculate the critical disruptive voltage and corona losses. Okay. So first one is uh, uh, okay, options are there: 90 and 0, and another one is 50 and 75. This is kV, this is kilowatt, this is kV, this is kilowatt. Then 110 kV, 0 kilowatt, and D, none of the above. So give me the right answer in the chat box. What you have to do, you have to calculate the critical disruptive voltage and corona loss for a three-phase line which is operating at a 110 volt kilovolt, which has a conductor of 1.25 centimeter. So you have to calculate this. I'm waiting for the answer in the chat box. Anyone try to solve it? No one. Okay. So what happens here is that we know the formula to calculate the critical disruptive voltage. What it is? V is equal to V is equal to here I am writing the dielectric strength is 21, okay, and the radius of the conductor, what it is? The radius of the conductor is 0.625, okay, which 1.5 divided by 2 into delta is 1.07 log d by r. So in centimeter, 3.05 meter will become 305 centimeter divided by R, which is this much. So critical disruptive voltage comes out to be 21 into 0.625, 1.07 into log. This value will be, I think, this value will be 6.19. So if we see here, it is 87 kV. So the critical disruptive voltage comes out to be 87 kV. Now, line operating voltage. Line operating voltage. We will calculate first. What it is? It is 87 into root 3. Sorry, just a second. Operating voltage is already there. Line to line voltage is line to line voltage is 87 root 3. If we calculate it, it comes out to be 150.66 150.6 kV. But the line is operating at how much? 110. So basically, the corona losses will not be there because it's already operating below the line to line voltage. So that's why the corona loss will be 0. Okay. Now, another question. Question number 2. A single phase overhead line has two conductors of dia 1 centimeter with spacing 1 meter. Dielectric strength of air is 21 kV per centimeter. Determine line to line voltage. Sorry, determine the line voltage for which corona will occur. Okay. So option A is 56 kV, B is 90 kV, C is 33 kV, D is none of the above. Okay, so you have to give me the answer. So you have to give me, you will calculate what the critical disruptive voltage, and we have to give the line voltage. So that critical disruptive voltage will already become the voltage at which the, yes, just like that. It's I have approximated to 56 just for the ease. Otherwise, the answer is 55.6, 55.36, sorry. Okay, so yes, so it will come out to be A option. So first, what we will do? First, we calculate disruptive voltage on the similar lines by 21 into all those values, and based on that, you can calculate the answer. It's a simple question, nothing like this. Okay, now question number 3. Corona laws. You should give the answer in the chat box. Okay, these are MCQ based. At least try to participate. Particular system at 50 Hz is 2 kilowatt per kilometer per phase. P loss, P corona loss at 60 Hz in the same system. What will it be? First, uh, just a second. One improvement. This is 1 kilowatt. Okay, is 1 kilowatt per phase. So basically 0.833, B 1.23, C 1.13, and D is 2.13. We have to calculate the answer. So give me in the chat box the correct answer. Does anyone? Okay. So it's a quite easy question. We know that P is directly proportional to F plus 25. Okay. So we have to get P60 divided by P50 is equal to directly proportional. So 85 divided by 75. So if we rearrange for P60, it will 85 divided by 75 into 1. So it comes out to be 1.13. So this will be the answer. Okay. Yes. Yes. Okay. Question number 4. The good effect of corona of on overhead lines is first increases the line carrying capacity. B. Increases the power factor. C. Reduces the radio interferences. D. Reduce the steepness of surge front. So give me the correct answer. Good effect of corona. What is this? So what happens here is that the corona has, I have already told you, it has various bad effect like undesirable effect. First, it reduces the current carrying line carrying capacity, or it also increases the power factor. So these are all the, and also increases the radio interferences. Okay, so these all are the, all increase all are the bad effects or negative effects of corona. But in the question we have been asked, what are the good effects? The good effect is that it reduces the steepness of the surge front. For example, like during any lightning strike or switching operation, what happens here is that high voltage surges travel along the transmission line, and what due to these surges due to these surges, they have a steep wavefront which poses a significant threat to the insulation or any other equipment. So what happened here is that the ionized air around the conductor, what it will do, it will reduce the effect of steepness by creating a cushion, or although it helps in smoothing out the energy, and it will result in the lesser severe surges, which likely to cause a less damage on the insulation. So therefore, as per the question, the fourth option is the correct one. Okay, so let me solve it another question for you. So another question is here. Okay, now question number 5. What it is? Just a second. It is given in the question, the insulation level of 1200 kV EHV overhead transmission line is decided on the basis of first switch switching over voltage, B, lightning over voltage, and C, corona inception voltage, D, none of the above. So write in the chat box the correct answer. So how we are going to decide any extra high voltage overhead transmission line? The insulation level. It is on either on the basis of switching over voltage, either on the basis of lightning over voltage, or the corona inception voltage. So you have to give me the answer to this. Okay, I think none of you have sent me an answer. Three. Yes, yes, correct. So, whenever we decide the insulation level of EHVs, okay, extra high voltage, we always decide the insulation on the basis of switching over voltage, never using the lightning over voltage. Okay, this is the one of the important thing. Now, question number 6. An overhead transmission line having surge impedance of 250 ohms and bifurcate into two branches of surge impedance of 120 ohm and 160 ohm. The traveling wave if the traveling wave of magnitude 220 kV travels along the overhead line, calculate the magnitude of current reflected back into the overhead line after traveling wave reach the junction. So in this you have to calculate this. So basically, so so what we have to do here in this, what happened here, a, one overhead line, okay, having the surge impedance of 250 bifurcates into two lines, and these two lines have the surge impedance of 160 and 120. So we have to calculate, and the traveling wave ER, the traveling wave has a magnitude of 220 kV. It travels along the overhead line. So there will be some some of the waves will get transmitted and some will be the reflected back. So first we will calculate the transmitted voltage. So the transmitted voltage, let's say this is E T is equal to, we already know, 2E divided by ZC plus Z1 Z2 divided by Z1 plus Z2 into Z1 by Z2 upon Z1 plus Z2. Just a second. Let me increase, let me see how it is coming up. Okay, first. Because it's a direct formula. I hope you know that. So here, what happens here is that, let's say this is, its equivalent is like this. Okay, ZC. Okay, now it goes into Z1 first surge impedance, then Z2 another surge impedance, and let's assume the transmitted voltage across there is ET. Okay, and the current traveling here is that, like, transmitted current 1, in this branch the transmitted current 2. Okay, and this is 2. Okay, so this is the equivalent structure or equivalent circuit of the branch on the left side, on the right side. Okay, so from here we know that ED, this is ED, is equal to how much, by using the voltage dividing rule, 2E divided by total impedance, which is 1 upon Z1 plus 1 upon Z2, multiplied by the impedance. So here will be Z1 Z2 upon Z1 plus Z2. So ET 2E, E is 220 into Z1 120 into 160 divided by ZC, it is given 250, and plus 1 upon Z1, let's say this is Z1 plus Z2 divided by Z1 Z2. Okay, so instead of that I am writing the values. It will be 120 into 160. Just a second. It is actually voltage, it is Z1 Z2 divided by Z1 plus Z2. Okay, the equivalent resistance, equivalent impedance of these both two. Okay, it will be added in series with it. So basically it will be 120 plus 160. Okay, and I hope so. Okay, so if we so let's rearrange this also. Multiply it here, 120 plus 160, and you know that these two will get cancelled out if we multiply this here, and it will come above. So basically I'm not writing that here. So the simplified expression will be this one: 250 120 plus 160 plus 120 into 160. What I have done here, I have just multiplied ZC by Z1 plus Z2 and move it toward the numerator, and both will be cancelled out. These both will be cancelled out. So if we solve it, the transmitted voltage will become out to be 94.7 kilovolt. Okay, now if we are going to calculate the transmitted current in the first branch where it bifurcates, let's say this is IT1, it will be equal to the voltage across that branch divided by its impedance, which is the surge impedance. voltage we just calculated divided by the impedance. Let's say it is first one has 120, so it will become out to be 0.789 kiloampere. And basically, similarly on the similar line, we can calculate the transmitted current in a second, which is just 94.7 divided by 160. It will come out to be 0.592. So what happens here is that, but first we will calculate the incident voltage, incident current which is coming toward the junction. It is, let's say this is I and it's equal to E divided by ZC. What is E? 220 divided by its surge impedance. So it will come out to be 0.88 kilo ampere. So what happens here is that a current is coming, it is reflected, some of the current will be reflected back, some of the current will be transmitted in these two, and this is the incident. Okay, so how we are going to calculate uh, the reflected current, reflected current. So the incident current is equal to IT1 plus IT2 plus IR, because this much amount current will be coming, some of portion will get transmitted to over here and over here, and some will be reflected back. So basically IR will be equal to I, just a second here, as per the rule convention it should be in minus because it is in different direction, so that is minus. So from here we can say that IT1 plus IT2 minus I, because this is coming in this direction. If we are taking this as positive, then IR will be in the minus. So IR will be equal. What is IT1? We just calculated 0.789, 0.592 minus 0.880. So if we add up and solve it, it will come out to be 0.501 kiloampere or 501 ampere. Okay, so the reflected current which we are asked in the question is 501 ampere. Okay, so I hope you have understood this question clearly. This is how we are going to solve the question. Now, question number 7. Which of the following statements, which of the following statement is correct when a rectangular surge wave travels along a line terminated by inductance. Okay, first option is the voltage across the inductor initially decrease to double the value of incident wave and increases exponentially. Okay. V is the voltage across inductor. The voltage across the inductor initially rises to double the value of incident wave and decays exponentially. C. Inductor act as a short circuit. D. Both B and C. So give me the correct answer, what it will be. Okay, so what happens here is that whenever a line is terminated by an inductance, what happens here is that its value increases to the double of the incident value, and after that, after the energization of the inductance, its value decreases, but it decreases in an exponential way. It is not right. It increases exponentially. It is not right. Act as a short circuit. It is also not right. So B is the correct answer to this question. Okay. Now, question number 8. 100 kV rectangular surge wave travels along the lossless line trans lossless line terminated by an inductance 6.5 millihenry. Determine the magnitude of voltage in kV across the inductance. After 10 seconds, if the surge impedance of line is 250 ohm, A 62 to 65, B 78 to 81, C 94 to 97, D 103 to 106. So you have to give me the correct answer. I'll wait for few minutes. You have to solve it. Then we will see which one has given the correct. Now solve this question number 8. It's a very simple question. Just told you about this, that whenever a surge is impedance or terminated by inductance, the voltage will be how much 2V will be stored, and after that it will decay exponentially. So in this question, ZC is given 250 ohm, L is 6.5 millihenry, and V is 100 kV, and T is equal to 10 seconds. So voltage across the inductor, what it is will be, it is, let's say, VLT. So we know the standard equation of the voltage across the conductor V, and let's say this is V 0, 1 minus E minus T by tau. So here what it will be like, this is 2V, this is R, sorry, this is Z, and this is inductor L. Okay, so the constant tau will be, how we will define tau? Tau is equal to L by Z, which is this. So 6.5 into 10 raised to the power minus 3 divided by 250. So it will come out to be 26 microsecond. Now V naught is already giving the maximum voltage. Here it is 2V. I have just discussed that. Okay. So now what we will do here, so VLT is equal to 2V. Okay. What is V? V is already given 100. So I'm writing directly 100 over here. 100, 1 minus E minus T by tau, which is 26 microsecond. So, but we have to calculate at T is equal to 10 microsecond. So VLT comes out to be 200, 1 minus, what is T? 10 divided by 26. So this much voltage will be there. So now if we using the calculator, if we solve this, it will come out to be, let me see how much it is. It will come out to be VL at 10 microsecond comes out to be 63.86 kV. So if we go back towards the question, the first option is the correct one. Okay, this is how we should solve the question. Now question number 9. A 160 kV rectangular wave. It travels along the lossless line terminated by terminated by inductance. of 10.5 millihenry. Calculate the reflected voltage reflected voltage wave after 10 microseconds if the surge impedance of the line is 280 ohms. So basically the options here are A plus 64.7, B minus 64.7, C plus 85.1, and D minus 85.1. Okay, okay. So I will solve it for you. So what is given in the question here is that there is a line whose surge impedance is 280 ohm, and it is terminated by a inductance of 10.5 millihenry having the voltage 160 kV, and we have to calculate the reflected voltage at the 10 microsecond. Okay, so we know that first of all what happens here is that the inductance will get charge up to the voltage 2V, and then after that it will decrease the voltage. And the voltage will get decrease exponentially. So whatever the decay of the voltage will be the magnitude of the reflected voltage. So magnitude of reflected voltage is equal to 2V e minus t by tau minus V. Okay, which is the incident voltage. So basically here tau is equal to L by ZC 10.5 into 10 raised to the power 3 divided by 280. It will come out to be 37.5 microsecond. So we have to calculate the reflected voltage at 10 microsecond. So 2 into V is 160 into E minus 10 divided by 37.5 minus 160. So the reflected voltage will be like this. So if we solve it by using, yes, it will come out to be around 85.1 kV. Okay, like this. So the magnitude will be positive, and the correct answer will be C. Yes, yes, 85.1. It's almost like round off value. Okay, so question number 10. The voltage in kV of 2.75 per unit basic insulation level for a 320 kV transmission line. So this is the options: 627, B 651, 654, C 680 to 682, D 717 to 720. Okay, so give me the correct answer of this question. Okay, let me see others. So, the voltage in kV of a 2.7 basic insulation level of the 320 kV transmission line is, it is 320 into root 2 divided by root 3, okay, into 2.75 per unit. If you multiply it, it's a basic thing, okay, and it will come out to be 718.1517. It will be the correct answer, D. Okay, now question number 11. 400 kilovolt 2 microsecond rectangular pulse, sorry, rectangular surge on a lossless line having surge impedance of 300 ohm approaches a station at which the concentrated earth capacitance is 20 nanofarad. Calculate the reflected voltage wave in kV. Option A is minus 136.5. Option B plus 136.5. D minus 173.2. C D plus 173.2. Okay. Now here what happens here is this. It is terminated in a capacitor whose value is 20 nanofarad. So you have to give the reflected value answer in the chat box. So I will solve it for you. So what is given in the question? It is given that a surge impedance of the line of a lossless line having 300 ohm. Now it is approaches a junction which is a capacitance, which is a concentrated earth capacitance. So basically, it is terminated into a capacitance whose value is 20 nanofarad. Okay, and what happens here is that we have to calculate the reflected voltage value. The reflected voltage is equal to VRT is equal to V transmitted minus capital V. So what happens here is that VRT is equal to V transmitted is this much energy, okay? because this much voltage will be in the capacitance. So T, first we will calculate tau. Tau is simple, ZC. What is Z? 300 into 20 into 10 raised to the power minus 3. So it will come out to be 6 microsecond. Okay, these three will cancel out. So 6 microsecond. So VRT, and we have to calculate at T is equal to how much? At what? Just a second. 2 microsecond. Okay. So 2 into 400, 1 minus E, T2 minus 6 minus 400. So it will 800, 1 minus E minus 2 by 6 minus 400. So if we solve it, it will come out to be 173.23 kV. Okay. No, no, no. It will come out to be this much in minus. Okay. Check your calculation. Maybe you have calculated wrongly. No problem in that. So the correct answer will be how much? C, minus 173.2. Okay. Now let me give you some more questions so you can. Now another question. Question number 12. The corona effect can be minimized by increasing. Options are: first, length of conductor; B, spacing between conductors; C, diameter of conductor; and D, both spacing and the diameter. Okay, so what is the answer? Yes, yes. So give me the answer of this, which is the correct. No one. Actually, both the spacing and the diameter, the corona effect can be minimized. I have already just told you about that, how we are going to reduce the effect of the corona. So question number 13. There is a factor in the corona which is the irregulatory factor. So what happens here is the irregularity factor, and for different types of for polished wire, it has been asked here. So what is the irregularity factor for the polished wire? We should know. Okay, what it is? There are options: 0.83 to 0.87, B 0.93 to 0.98, C 0.80 to 0.85, and D 1. So what is the correct answer? Please give in the chat box. So basically, for a polished wire, the irregulatory factor is 1. So I will explain you how. So how it is integrated. So basically, what happens here is that we have just derived the equation of the disruptive critical voltage, which is G naught delta log D by R. But here there is another term which is known as M, which is generally used. M is the surface factor or irregularity factor. Okay, what it does actually, it is the measure of smoothness of conductor. Okay, it also what happened here is that what happens here is that for different types of conductor, for different types of conductor, its value is different. Okay, like for any polished one, which is just I have asked the question, it is 1 for polished and smooth conductor. Okay, but for any rough and stranded, its value ranges from 0.93 to 0.98. Okay, for the rough and stranded conductor. Okay, for 7 stranded conductor, its value ranges from 0.83 to 7 stranded cable. Okay, so these are some of the values. Like I will give you some more value. Like just a second. Yes, for more than this, for more, if the cables are have more than 7 strands, its value ranges from 0.9. For more than 7 stranded cable. Okay, so in order to have a more practical expression, we generally include this M, which is known as the irregularity factor. Okay, so now let me solve it another question. I will give you another question. Okay, so we will solve one more question. Next question, like what is this? Let me solve it for you. Question number 40. Okay. A 200 kV and 4 microsecond rectangular pulse. Rectangular surge on a lossless line having a impedance of 250 ohm approaches approaches a station of concentrated capacitance 30 nanofarad. Determine the magnitude of transmitted current. Before that, we have calculated the reflected voltage, but now we are going to transmitted current in the capacitor. Okay, so these are of the options. One is 1.6, it is in kiloampere. B 0.94, C 0.83, D 0.72. So the solution to this is, what is given here, 250 ohm is the surge impedance, C is 30 nanofarad, V is 200 kV, and TD is 4 microsecond. Okay, so we have to calculate the transmitted. First, we have transmitted wave voltage. So transmitted voltage will be Vt is equal to how much? 2V 1 minus Et by tau. Okay, and the current which will be transmitted into the capacitor will be equal to transmitted current. What it will be? It will I is equal to C dVc by dt. So we will differentiate this. So It is equal to C. What is dVc by dt? It will be Cv into E minus T by tau. It will come out to be this one. So it will be equal to how much? Just a second. Just a second. It will be C into 2 into E minus T by tau into V, okay, and divided by tau. So it will come out to be 2 CV by tau E minus T by tau. It is the transmitted current into the capacitor. So here tau is equal to Z into C. What is Z? 250 into 30 nanofarad comes out to be 7.5 microsecond. Okay, and after that we have to calculate IT at t is equal to 4 seconds, because it is given a 4 second rectangular surge is going on. So at 4 seconds it will be 2 into C. What is C? see his here 200. Just a second. It is uh, tau. How much we calculated? 7.5. Okay. So we will be doing what we will doing here. C into just a second. Okay. Okay. Yes. Yes. It just mm. At t is equal to 4 microseconds. So I t is equal to 2 into c 30 into 10 raised to the power minus 3 divided by tau, which is for how much is 7.5 microsecond, into V, which is how much voltage is here, 200 kV, into E minus 4 by 7.5. So if we solve it for the IT, it will come out to be 0.9386 kiloampere, which is generally equal to 0.94 kiloampere. Okay, yes, it will come out to be like this. So the correct answer to this question will be 0.94. Okay, so now next question here, question number 15. A 300 kilometer long transmission line, okay, of surge impedance 260 ohm is terminated at a substation. A 400 kV surge travels through the line and voltage at terminal of the surge arrestor at the dead end is found to be 280 kV. Find the find the discharge current in the arrestor. A is 2, B is zero point 0.5, C is 1, D is 2000. So we have to calculate which of the following is the correct answer. So basically the discharge current in the surge arrestor is I surge, denoted by, is equal to 2V minus V surge arrestor voltage divided by its impedance. So what is 2V? Here is V is 400, to 2 into 400 minus arrestor voltage, which is given here, is how much? It is 280 volt, because line voltage at the surge at the dead end is found to be 280. So 280 divided by impedance, which is 260, the surge impedance. So it will 800 minus 280 divided by 260. It will come out to be 2 kilo ampere. So if we calculate the discharge current, it will be option D 2002 m. Okay, 2000 amperes. Okay, so now we will solve another question, which may be the last one of this session. Question number 16. I will provide you all these notes. You can go again if you have not got a idea how are we going. If you miss anything, you can go again through these notes, which will help you in understanding. So a line of lossless transmission line with surge impedance 400 ohm have a have a have a terminal load considering of parallel combination of parallel combination of 0.01 microfarad and 10 kilo ohm resistance. A surge load, a surge voltage in the form of unit step function of 250 kV magnitude travels along the line. Find the load voltage. We have to find the load voltage 10 microseconds after the arrival of wave front of surge. Okay, so what is given here? I will. This is a wave front surge of E. ZC it is terminated into a parallel combination of capacitance and the resistance, and this capacitance is initially discharged. So ZC is given how much? 400. C is given zero point zero 0.01 microfarad, and the resistance is given 10 kilo ohm. And E, which is the voltage unit step function voltage, it is coming with the magnitude of 250 kV. So the time constant of this equation is the circuit is tau is equal to equivalent R equivalent into C. R equivalent, just a second. Okay, so basically R equivalent how much we have to calculate. Why? So R equivalent, these two will be in R and ZC will be in the parallel. So R into ZC divided by R plus ZC into C. So basically 10 raised to the power 4 into 400 divided by 10 raised to the power 4 into 400 into 0.01, because the C is 0.01 microsecond. So basically it will convert it into the microsecond, 3.84 microsecond. So the load voltage, which is E, will be equal to ET0 1 minus E minus T by tau, where ET is क्या है? ET is the voltage at the load end when the capacitor is in the open circuit state. So ETO पहले हम निकालेंगे So ETO will be equal to 2 times E multiplied R upon R plus ZC. So 2 into 250 into R, which is 10 raised to the power 4, divided by 10 raised to the power 4 plus 400. So ETO comes is the value when the capacitor is open circuited. So it will come out to be 480.76. Now, if we calculate ET at t is equal to 10 seconds, so what it will be 480.76 into 1 minus 10 by 3.84. Let's take this value. We just calculated the time constant, and ETO will be this much. So if we solve it, it will come out to be 445.05. So basically, the load voltage after 10 seconds will be equal to 445.05 kV. Okay, so I hope you have got an idea how to solve these questions, because these are very complex questions, and you should know the various formulas, like how we are going to calculate these E or various discharge current. Okay, so I hope this makes you understand how we are going to calculate this. And with this, I end today's session. If you have any question, you can ask. These notes and solution will be provided to you. So with this, I end today's session. Thank you for your joining. We will meet again in the next session next week. Thank you.